Okay, differentiability. What does that mean? What am I referring to, do you think? The ability to differentiate a function, right? So we want to know where can I differentiate a function and where can't I differentiate a function? If I ask where a function is differentiable, it means where can I calculate a derivative? Where does it have a derivative? Okay? There are some places where it doesn't have a derivative. Okay, so let's, just to kind of define our parts of calculus speech here, derivative is a function that outputs the slope of a curve, meaning the slope of tangents to the curve, at values of the input. That's a noun. Okay? That's a noun. To differentiate is to take the derivative, meaning to derive the derivative function from the original function. That's the verb we use. We don't use the word derive. You don't derive a function. I mean, in this case, I'm using the English version of the word derive, meaning I'm going to start with a function and I'm going to go through a derivation process and come up with the derivative function. But the verb we use is to differentiate. When you talk about taking a derivative, you're talking about differentiating a function. So differentiability is take the derivative ability. Where can we take the derivative? So there's a couple important concepts here, and this is a huge one. This is one of the most important statements we can make in calculus, is differentiability implies continuity. And notice the 3 exclamation marks. That's how important it is. It wasn't even, not 2, it needed 3. Differentiability implies continuity. So if a function is differentiable, it's necessarily continuous. Okay? But the converse is not true. Just because a function is continuous does not mean it's necessarily differentiable. Okay? Does not work both ways. And we'll see why. So what are the places where functions fail to be differentiable? Where we can't take derivatives? Well, discontinuities. Okay? Or other places where limits don't exist. Because remember, the derivative fundamentally relies on the existence of a limit, doesn't it? Right? So discontinuities are places where the derivative is not defined. Sharp corners are places where derivatives are not defined. And how come? Well, we'll talk about that. We'll look at some examples. And then vertical tangents, which could be places where you have, infinite discontinuities, or they could be places where you have cusps, where you have, and we'll look at an example of that too. A cusp is just a place where the derivative approaches infinity, but the function is still continuous. Okay? So we'll look at each of those in turn and kind of scrutinize them. So what about this? What about that first one? F of x equals the ceiling function, ceiling of x. Or actually, that's the floor of x, never mind. Floor of x. Okay? Or a greatest integer function. Where is that function not differentiable? This guy. Yeah, at each integer, right? Because at each integer there are breaks in the function, there are discontinuities, and so the function is not differentiable at every integer value. Okay? How about this one? This one is not differentiable at 0 because there's a break in the function at 0, right? It's discontinuous there. No. Right? Differentiability implies continuity. For the function to be differentiable, it must be continuous, and those functions are not continuous. Okay? Give me thumbs on that. Is that making sense? Okay? Okay, how about that one? Where is that one not differentiable? 0. Okay, and there's a reason for that. If an ant, and our ants now, I haven't told you the full story about these ants. The two-dimensional calculus ants, they have the ability to sense their x and y coordinates in the plane, but they are really sophisticated. They've evolved the ability to sense their slope as well. Okay, so an ant that's walking along the left leg of this absolute value function, as he walks closer and closer and closer to x equals 0, what slope is he sensing? Well, I mean, as he's walking down this leg, he is sensing a slope. What is it? -1, right? That makes sense? I mean, because isn't he like rising -1 and running 1, right? And he senses that. He senses that, okay, my slope is -1. So he anticipates, as he moves towards 0, he anticipates a slope of -1. That's the slope he's experiencing. What about an ant walking from the right? Well, he's experiencing a slope of +1 and anticipates a slope of +1 when he gets to 0. Well, okay, who gets to choose? Should either one of those ants have a preferred reference frame there? Why? There's no reason, right? I mean, you could say that our two-dimensional spaces should be isotropic, meaning all directions are the same. And so we shouldn't be able to assign a preferred directionality here. And so therefore, the derivative can't exist at 0 because they would disagree. And neither one of them should get to decide. And so neither one of them gets to decide, right? Make sense? The derivatives from the left and the right are different, and so the derivative doesn't exist at that sharp corner. You can't have a place where the derivative instantaneously changes, okay? And let's see, did I have a cusp? I think I got this a little bit messed up. Well, what about a cusp? Do I have a cusp in here somewhere? Yeah, there's a cusp. That's a cusp. Okay, what does that mean? It means that as an ant approaches from the left, he sees the tangent line becoming more vertical. And so he's seeing a slope of -infinity. The ant who's to the right of that point is going to be anticipating a slope of +infinity, and they don't agree. In fact, I can't even have an infinite slope. So another place where tangent lines, I don't know if I even wrote that one on there. Another place where derivatives don't exist would be places where we have vertical tangent lines. For what reason? What have we always said since probably Algebra 1 about the slope of a vertical line? It's undefined, right? So if the derivative's undefined, then it can't exist there, because that's the job of the derivative, is to tell us the slope of the function at that point. So if the tangent line is vertical, the derivative doesn't exist. So for multiple reasons, at that cusp, there's no derivative. For one thing, because they don't agree on the slope of the function, but also because it becomes infinite. Okay? He would. He'd see it as positive. The ant from the left would see it as negative. Because look at that tangent line. If we smoothly migrate that tangent line from positive values to more positive values to more positive values, it seems to be approaching a really large positive value, which is positive infinity. See what I'm saying? Well, the other side, the ant is seeing negative values, increasingly negative values, increasingly negative values, and so he's anticipating a value of negative infinity. Okay? But in a sense, both of those are irrelevant, because both of those involved infinity, so who cares? If it's infinite, it can't exist anyway, right? Okay, so I'm going to throw another concept at you here that is not in our textbook, but I just want you to be kind of aware of, and that is the concept of one-sided derivatives, because this is useful later on in your mathematical life. A derivative from the left, or a left-handed derivative, just says this. All it is, notice the notation, f prime of x from the left, right? I get that negative superscript. That just means if we're approaching some value where h is a negative value, right? So instead of the point, like we had the point on our graph, we had x and then we had x plus h. H was assumed to be positive. What if h was negative? Well, then it would have been over here. The point would have migrated to the point x, f of x, from the left instead of from the right. That's all we're doing. We're just migrating the 2 points that create the secant line. We're either going to migrate a point from the left to join up with a point, or we're going to migrate it from the right. Well, if we're calculating a derivative from the left, then we're migrating that point from the left, right? We're just taking the limit as h approaches 0 from the left. H is a negative number that's approaching 0, okay? Derivative from the right, well, we'd assume a positive value of h. Okay, what's the point of that? Well, that can be useful. Like, for example, this function right here at -2 only has a derivative from what direction? The right. Agreed? Because it's an endpoint, and so that has to be a one-sided limit. If we're going to define a derivative at -2, it has to be a one-sided limit that we're using, because the function doesn't exist to the left of -2, right? So when we do our limit of the difference quotient, you know, we would have to use that guy. We'd have to, right? Because the limit h could only approach 0 from the right in this case, okay? Give me 1 to 5 on that. Does that make sense? So it allows us to say that, okay, this function is differentiable from -2 to infinity. Okay? It just saves the day. It allows us to label that endpoint as being a place where it is differentiable in the sense that it's a derivative from the right. It's a one-sided derivative. Okay? How about something like this guy right here? What is f prime of x from the left? Okay, well, let's figure it out. It's a piecewise function. So if I'm approaching, really what I'm trying to do here is I'm trying to say at 2, right? We're trying to calculate, I should make this f prime of 2 from the left. Well, which piece are we talking about there? The top piece or the bottom piece? Top piece, yeah. So that's going to be the red piece. Okay, so then let's just calculate the derivative in general from the left. So we'd have to write it that way, wouldn't we? Right? Okay, what's that going to be? Limit of, okay, so f of x, so that's going to be right x plus h, right? Let's write it out. I want to write it out. Limit of f of x plus h minus f of x over h as h approaches 0 from the left. Okay? So what is that? Wasn't that just 2? It was 2x was the function there, right? So it's going to be the limit of 2 times, instead of x, I'm going to have an x plus h, right? Minus 2x over h as h approaches 0 from the left. Well, that's just going to be 2x plus 2h minus 2x, right? Well, look, these guys cancel horizontally. What happens to the h's? They go away. And so don't I just get the answer, this is equal to 2? Right? So f prime of x from the left is the constant value 2. Okay? So ants approaching, x equals approaching 2 from the left would anticipate a slope of 2. That makes sense. That's a line with a slope of 2, isn't it? Right? Okay, that's a good place to stop, I think. We'll wrap this one up tomorrow.